Hey guys, welcome back to the channel and welcome back to yet another exciting video. And we will be continuing this series on build your own X. In the last video that we saw, we built our own tokenizers wherein we just gave a string as an input and we get the tokens that are generated. Now, adding to that, in this video, we will be building our own embedding. Okay, so kind of we can say we are deep diving into the world of AI, how things under AI are working. So we'll be using some of the different ways to generate our embeddings, where we'll be learning about TF-IDF, bag of words, co-occurrence, matrix, and much more things. So without any further delay, let's get into the computer screen and let's start with understanding what are embeddings first. Okay, so before moving forward, I would just like to say that we have a complete new playlist which is going on currently on our channel, which is Building Your Own X. Okay, so this is where we are starting to build our own stuffs. Like we started with you starting with Git. Now we are under tokenization. In this video, we will be watching about the embeddings first. And we also have our build X site, we can say, where the new episode is live and also the explanations are live. You can just give an input like low for tokenizer, low, lower, and lowest. So this is where you get a complete animated way of how things are working. Like it will give you the buffer bytes and applying the merge rules, each and everything one by one. So it will become very easier for you guys to understand how things are working internally in this particular concept. Okay. And even if you want to watch the video is also linked. You can watch and understand things side by side. Okay. So let's get into the next part where we are understanding about what are embeddings. So let us start with this. I'll just close this for now. Okay. So let me ask you a simple question. Okay. Uh, we have a car. Okay. And we have a word which says automobile. Automobile. Okay. As humans, we know these things are same, right? Because car comes under an automobile, bike comes under an automobile, a truck comes under an automobile. But how does the computer understand that this and this are the same, right? Computer does not understand words. Okay, they only understand 0 and 1. Everything for them is just under numbers. Okay, this particularly includes the car that we are talking about. This also includes the automobile that we are talking about. Okay, let's take a very simple example. In terms of computer, it would not see car as a word. It would see the car as something like, say, 011 011. Okay, it would see the car in this particular format, which is in the form of zeros and ones. The same thing would go for automobile, where it would be seen as zero, not two, two, double zero, triple zero, double one, triple zero. Okay, something around that. So this is what we learned where we talked about tokenizers, right? Car would be in this particular format under buffer token, and the same would go for automobile. Okay. But when, let's say, I ask you a question, like we have a car and we have an automobile, do these bytes look similar? Let's say we have a car where we have the bytes given as 99, 97, and 114. These are, let's say, the tokens that we have, right? And we have automobile here, where the value goes like 65, 117, 116, 117, 109. Do you think these bytes look similar? Obviously not, because they are completely different. But yet, we as humans, we know that these both are similar. So bytes are clearly not enough for us. Okay. So let's do something. Let's invent something. Okay. Let's say we have our vocabulary as car, bike, plane, and boat. Okay. Let's say we have a basic assignment here that we do. The car here acts as the first element of the list here. Okay. So what we'll do is total number of list is 4. Okay, so we'll have 4 digits over here. And starting with the car, where we can say the element that exists at that particular index will have the value 1, others will have the value 0. Okay, so since car is at the first position, so we can say 1, and it is not present at the other indexes, so we can have 0, 0, 0. Okay, same goes for bike. Bike is at the second index. So the first one will be 0 and the second will be 1 and rest other will be 0. Same goes for plane. So it will be double zero, one, double, 1, 0. And the board will be 0, 0, 0, 1. Okay. This is what we have assigned here. And this particular thing that we see here is known as one hot encoding. Encoding. Okay, this is something that we are going to do build now. Before going that, we'll just have an understanding of what is one hot encoding, um, encoding. So as you see here, it says it is a data pre-processing technique that converts categorical text and or labels into numerical vectors. So let's start building our own version. Okay, so we'll have here, we'll create a folder nkdir build embeddings. Okay, cd build embeddings. And inside that, we'll have a folder with the name lib. We'll have all the libraries, not tokenizer, lib. And inside that, we'll have a first file, which will be an one hot encoding method. Okay, so the first thing that we'll have here is to have an interface, export interface, one hot encoding result, where what we will be doing here is we'll be having the vocabulary, okay, which is what we defined here. So we'll have the vocabulary here, which will be a string, array of a string. And next we'll be having the vectors. Vectors are basically a record where we have the string and a number. Okay. Okay. This is the interface that we defined. Now, the text that we give, the first task will be to build vocabulary. Okay. Please don't go over the spellings here. So we'll have a export function, which will say build vocabulary, where we'll be passing the text in the form of a string, which will be in the form of a string array. And we'll just return a new set, like we'll be copying it with the spread operator, where we have the new set, where the text that we have, firstly, we'll be converting it into lowercase. Okay. Then we'll be splitting it. Okay. And then we'll have the filter and we'll have the filter with the help of booleans. So we'll have boolean here. Okay. So this is the one where we build the vocabulary. Next is to create one hot vector for each word. Okay. So we'll have export function one hot encode, where we have the text as string and the output type would be a one hot encoding result. The first thing, to create the vocabulary, and we'll have build vocabulary and we'll pass the text here. Next is to have vectors created, which will be of type record, of string, and an array of numbers, which will be the representation that we saw here. Okay, it will be of the type string and an array of numbers for each of the input or each of the input text that we have over here. And initially we'll initialize at a empty object. And next, once we have the vocabulary ready, what we'll do is we'll iterate over each, like using the for each loop, where we'll have the word along with an index, and we'll say first, let's say const vector equal to have a new array, where which will be of the size vocabulary dot length and fill them with 0. Okay, initialize an empty array and fill them with 0. And for all those vectors where we have the index, keep it as 1 while iterating it. And then vectors of where we have the word present, we equate it with vector. And once we are done with this, what we'll do is return the vocabulary as well as the vectors. Okay. Next, let's say once we are done with this vocabulary, not this vocabulary, the spelling would be like this. Okay. Once we are done with this, let's try this. Let's say we have something like cons result equal to one hot encode, and the text says like the cat drinks milk and the dog drinks water. Okay, and what we'll be doing here is, let's say we just have it on console log the result. Okay, and I'll do one thing. I'll have the terminal here. Okay, I'll increase the size here. Okay, cd desktop dev build x from scratch YouTube ls cd build embeddings and go inside lib. Okay, now that we are using TypeScript, what we'll be doing here to run TypeScript is npx tsx and then the file name. Okay, so based on what we say, like the input that we have here, which is something like the cat drinks milk, what should be the output? It should be something like this. If you see here, the first thing that it did is it took the entire sentence and converted into vocabulary, like separated them with the words. Okay, we have the words the cat drinks milk and dog water. It's basically what it is doing is it's not taking the repeated words, it's just taking the unique words. And if you see here, the total number of words that are present are 1, 2, 3, 4, 5, 6, 7. And the vectors, the number of elements that we have is also 7. The stays at the first index, so the value here is 1, rest others is 0. For cat, it is at index 2, hence the value here is 1, others are 0. The same repeats for all the words that we have present over here. Okay, so this is basically what we do in one hot encoding. Okay, now let's say I'll ask you one another question here. Okay, let's say the car value is this 1000, and we take we add one another value, say automobile, whose value should be something like um, 0 1 triple 0. Okay, but are these vectors closed? Do you think are these vectors that we created close? Because this is 0 1, this is 1 triple 1 and triple 0, and it is 0 1 and triple 0. There is one additional 0 that is come here. No, they are not close. They are basically orthogonal in terms of maths that we see. So if we see here, the distance here is very huge. Even after we say the car and automobile are almost exactly the same thing. So this is where we say the one hot encoding fails. Okay. That is where what we do is we use something called bag of words. What it will do is basically it will count the frequencies across documents. Let's go here and search for bag of words. Okay. And we'll go here, we'll just increase this and understand. It's basically a simple fundamental technique in natural language processing to convert the raw text into numerical data for machine learning algorithms. Let's say the document one that we have here is the child makes the dog happy. The is repeated 2 times here and here. Rest everything is repeated 1 time. And the same thing for document 2 is the dog makes the child happy. And here if you see, it's like the word represents or is repeated 2 times. What they have done here is once we have created the frequency of the repetition of words, it's basically creating a graph or a table where we just write which are the words that are repeated, and then it is converted into vectors. It starts with the child dog happy makes and the, so it's like 1 1 1 1 and 2. So this is basically how bag of words work. Okay, so now we'll be building the bag of words library here. So we'll just create something like bag of words.ts. Okay. The first thing is to have an interface. I'll replace this with bag of words result, where we'll have the vocabulary as a string and vectors as an array of numbers. Okay, which will be a 2D array. And I'll remove this array. Okay. Next is the same thing, the vocabulary building. So we'll have building the vocabulary here, and here we'll have the sentences. Okay, and sentences will be in the form of a string. Okay, once we have the sentences, what we are doing is taking out the words by const words equal to new set of a type string. Okay, and once we have this, we'll have a for of loop where we'll be looping over the sentences, const sentence of sentences, and we'll have the sentence, and we'll just do the entire same thing, sentence dot to lowercase and then split. And instead of filtering it, we'll have a for each loop here, for each, where we'll have the word and add it under the words set that we created, words dot add word. Okay, and then we will just return a copy of words, return a copy of words. Okay, so this is the way we build the vocabulary for a bag of words, because it will be consisting of an array of sentences, an array of string. And once we build the vocabulary, next step here is to convert every sentence into bag of words. Okay, so basically the first part, to calculate the repeated words and then create a graph like, or a table like this. Okay, so we'll go with here and we'll create a function saying export function bag of words with sentences which are passed as string, like an array of string, and it will be of type bag of word result. First thing, to create the vocabulary, const vocabulary equal to build vocabulary, where we are passing the sentences. Next, to get the vectors, const vectors equal to sentence dot map sentences, not sentences, sentence. And then we'll also have small vectors here, const vector equal to new array, which will be of the length of vocabulary. Okay, and fill them with 0. And then we'll have the words, const words equal to sentence dot to lowercase, not to local, to lowercase, and then split them. Okay, we'll split it. After that, iterate over the words that we have and get the index, const index equal to vocabulary dot index of words. Okay, index of the word. Next, increment the value of the vector index, okay, by 1, and then return the vector inside the loop. After the loop is completed, we will just return the vocabulary and the vectors. Okay, and let's take an example here. We'll just copy this one. Where did it go? Yes, we'll copy this one, and we'll have bag of words, which will be an array of sentences. Okay, the first sentence we have is the cat drinks milk. Okay, the second would be the dog drinks milk, and the third one would be the cat eats fish. Okay, before executing, let me know what you think the output would be. Let me know in the comment section here. Okay, so I'll just clear this and say npx tsx, and we'll just try to run bag of words.ts. Okay, and when we press enter, the first thing is to get the vocabulary. Okay, And the next thing are the vectors that we got. Okay. If you see here, it's like 1, 1, 1, 1, and 0, 0, 0, 0. Okay. Because if you see the character, the word, or the word the is repeated only once. It's not repeated twice in a sentence. The is unique, dog is unique, drinks is unique, eats fish is unique. Okay. And if let's say if we add eats the fish, and we'll try to clear and have a bag of words. Now, if you see, the is getting repeated two times in the last sentence, which is the cat eats the fish. Hence, it is displayed two times over here. Okay. So, to solve the problem of one word encoding, we introduced bag of words, which helped us count the word frequencies across the documents that we have or the sentences that we have. But there is one more issue here. Okay. We can't keep track of all the word frequencies across many documents, because when the size of the documents increase, it becomes very difficult to understand and take care of all these things. For that, what we do is we introduce TF-IDF, which is basically to reduce the weight of the common words. So TF-IDF. What does it mean is term frequency inverse document frequency. It's basically a numerical statistics to reflect how important a word is to a document collection of corpus. Okay. TF-IDF is a measure of originality of a word by comparing the number of time a word appears in a doc within the number of docs the word has appeared in. Let's say we have a doc here. We'll take as example. Let's say we just take this example that we have here. Okay. The cat drinks the milk. Okay. Now here we can say we have total of three documents that we gave. Okay. That we gave over here. And for each of the document, when we talk about the word the, okay, it is repeated once in the first one, once in the second line, and the third, two times in the third one. But if you see, the is repeated once in first and second, and twice in third, right? It is repeated twice in third. But talking about the number of documents that we say is three. So that is where we compare if the particular word the is needed on the different documents as well. So how we calculate the TF-IDF is to first calculate the term frequency and then to calculate the inverse of the document frequency. The term frequency means the number of times the term T appears in a doc, and the inverse document frequency means the document frequency of the term T whose inverse we are calculating. Okay. This basically helps to reduce the weight of the commonly used words and help us understand if these words are to be used in our project or not. Okay. So once we define this, let's go here and let's create tfidf.ts. Okay. The first thing, obviously, to have an interface, copy this and have it as tfidf result, where we'll have the vocabulary, and instead of vectors we have the matrix, okay, which is of the style number. Next step, the first thing is to build a vocabulary again. Okay, I'll just remove these both. Build vocabulary where we have the documents in the form of string. Okay, the words will be replaced by, let's say, a new variable that we have vocabulary with a new set, and we'll have const doc of docs, and we'll have doc to lowercase, and then for each word we'll add it under vocabulary.add word and return vocabulary. Okay, the step for creating the vocabulary remains the same. Okay, next step is to create the term frequency. We'll have a function with the name term frequency, where we'll have the word which will be of a form string and the document which will be also a string and of the type number. So firstly, what we'll do is take out the words from the document, split them and convert them into lowercase. document dot to lowercase dot split, okay, and then have a count of the words, count equal to 0, initialize it at 0, and then iterate over the words that we have, const word of words, and say if, not the word, the token of words, if token is equal to the word count plus plus. Okay, meaning if we take this example where the is equal to the, so once if this is equal to this, we increase the number of count that we have here, like increment it with 1, and then we return the count divided by words, sorry, words dot length. Okay, so we created the term frequency. Now next step is to create the inverse document frequency. So we'll have a function with the name inverse document frequency, where we'll have the word as a string, documents as an array of string, okay, which will be of a type number, and have a document count. Like what are the total number of documents or the list of sentences of array that we are passing here, okay, and iterate over that and just count it. So we'll have for off loop, for off const document of documents, okay, and if document dot to lowercase dot split dot includes the word that we have word, okay, increment the document count, and then return math dot log. Now we have to return the base of that number, math dot log documents dot length, the length of the document divided by 1 plus document count. Because if you see, to calculate the IDF, we need to have the n document and plus 1 of that. Okay, so we created the IDF now, and next step is to integrate both. We can say tf IDF export function tf IDF, where we have the documents which is in the form of a string, and the type would be tf IDF result. Okay, the first thing, calculate the vocabulary. Let's say we have build vocabulary here, documents, and then create the matrix. Okay, we'll have documents dot map the document. Okay, and then what we do is we return the mapping of the vocabulary for all the words that we got, map word, and firstly calculate the term frequency, like const tf equal to term frequency with the word and document. Next, to create the inverse document frequency, like inverse document frequency with the word and documents, and then return the number that we get from TF multiplied by IDF and get a fixed value up to 3 digits. Okay. And once we are done with this, we just return the vocabulary and matrix that we converted. Okay. Now let us take an example here. Okay. We will take an example of something like this. Okay. We had this particular values or array of indexes, or not array of indexes, array of sentences that we gave as an input. Let's try to get this npx tsx, and this is tfidf. So the first thing, get the vocabulary. And now if you see, it is somewhat giving things in the form of matrices. Okay. So if you see, we have values like 0.056, 0.072. And if you have been into understanding what are embeddings, you might have seen the values are somewhat like this. When you go into your vector database and look into the embeddings, it's somewhat in this format. Okay. But now let's say if you as a developer or you as a computer also, we give the input like this, Do you see any similarity here? Are there any similarity or relationship between the words that we have or the matrix values that we have here? So I don't think so. So that's where what we do is we build something called co-occurrence matrix. Okay. So what it is basically a data structure that counts how frequency specific parts of item appear together when we are defining it under a spatial relationship. Okay. It gives like something like this, the co-occurrence matrix and individual contributions. So next step is to build the co-occurrence matrix. Okay. So for this, let me just give you the entire code here because it's a bit longer code. We'll have co-occurrence occurrence.ts. Okay. So this is how it looks like, where we first do a vocabulary creation and then we build the co-occurrence matrix. What we do here is we takes the size of documents that we have in the form of an array of string, build the vocabulary. Next thing is to get the index, okay, where we map it from the word and the index of the vocabulary that we got. And next is to create an array which has the length of vocabulary dot length and fill it with 0. Okay. Once we fill it with 0, then we iterate over the values of the documents that we have, split them, and then get the index words which are the target for us. Okay. And then once we get that, we iterate it inside for the columns where we get the window size. And if I equals j, we continue. Else, we get the context of j and create the matrix like target and the context plus plus. Okay. So how do we build the co-occurrence matrix for this one? Let's go into the terminal and try. I'll clear this and say npx tsx co-occurrence.ts. So if you see here, vocabulary is created, and now we are able to get something like a relation between the values or the words here, which because it is in the form of 0, 1, or 2. Okay. Now we have a basic relationship between the neighboring words that we see here. Okay. I hope you are able to understand things till now. The next step is the time where we start creating the embeddings. Okay. So embeddings basically help to convert. ये part निकालो. Once we are done with this matrix basically is not a good way that we take it. Like the entire big matrix is not a good option to go with. What we do here is we compress this. Okay, we compress the co-occurrence vectors into dense vectors. Okay, so let's go here and let's start building the embeddings part. Okay, we'll have embedding.ts where we are first taking the co-occurrence matrix and also take the co-occurrence result here. Okay, we'll also take the co-occurrence result from co-occurrence. Next, the first step here is obviously create interfaces because we are using TypeScript. We'll have embedding result. Okay, vocabulary of an array of string. Next is we'll be having embeddings, which is in the form of a record where we have the string and number in the form of a array. Next is to generate a random projection matrix. Okay, we'll just generate a very random matrix so that we can display it in the form of a UI. Okay, we'll have a random matrix where we have the rows, which is of the form number, and the column, which is also form of a not null number. Okay, and it will be a 2D array. And what we'll be doing here is we'll return array dot from the length as rows. Okay. It will be inside curly braces here, length as rows, and also map it from array dot from length as columns. Okay. And give us the math dot random value times 2 minus 1. Okay. This is basically where we are creating a random matrix. Okay. Next step is to go with matrix multiplication. If you are someone who is in college right now, you must have understood what is matrix multiplication, because in the SEM first and second, in maths 1 and 2, we go with the matrix multiplication. So today we are going to actually code it. Okay. So this might be something very interesting for you guys. The first thing is to take the vector input, which is the first array, and the second, which is a matrix, and the number of a 2D array, which returns you a number in a single 1D array. So let's say we have an output which is of the form array of number equals an empty array. Next, to have the dimensions in which we need to multiply. So we'll take the dimensions as matrix, the first index of the matrix, its length. Next, iterate over it. So let call equal to 0, call less than dimensions dot dimensions, and then increase the value here. Let sum equal to 0, for let row equal to 0, row less than vector dot length, and row plus plus, sum plus equal to vector of row into matrix of rows column. Okay. And we'll just put it under the array. We'll push it under the output array, where we have the number as sum dot to fixed of the value 3. Okay. And then return output. So this is basically what you guys solve in your matrix multiplication problems when you're given in your maths lectures. Okay. So this is what we have coded right now. Okay. So this is the first time you guys see the entire matrix multiplication getting coded. Okay. The next step that we do here, after we create the matrix multiplication, we compress it. We'll just compress it and build embeddings. Okay. And what we say when we, but what we mean when we say embeddings is, what we'll be doing here is we have, let's say we have something like this. We have access like this. And what we'll be doing here is we'll be displaying the values of the words like car, uh, bike, automobiles on a graph. Okay, it would be something like they are here, here, and here. Okay, so that's where we are building and compressing and building the embeddings here. So we'll have an export function which says build embeddings, which takes the co-occurrence as an input, which is of the type co-occurrence result. And also we'll have a dimensions as say 8. We'll have a 8-dimensional place here. And next is to first get the projection. We'll create a random matrix where we are passing the co-occurrence dot vocabulary dot length, the length of the vocabulary, and the dimensions. Once the projection is done, we create the embeddings, which are in the form of a record. Okay, we have a string and the number. The number would basically be the coordinates. Okay. Next is to build the matrix. So we'll iterate over the co-occurrence dot vocabulary dot for each will have the word and the index value, index, and we'll take the embeddings, the word of the embeddings, and multiply that embeddings from the co-occurrence, not co-occurrence dot matrices index with the projection. Okay, and then return the vocabulary, which will be the co-occurrence dot vocabulary and also the embeddings. Okay, so we'll not need this matrix, we'll just need that result. Okay, so this is where we built the embeddings. Okay, but there is a major thing that we need to understand here is how do we understand that embeddings are present, but are they similar to each other or not? As humans, we know that words like bike and automobile, bike and automobiles, bike and car are similar to each other. Taking a very simple example here, let's say in a graph that you have something like this, the word car lies here and the word automobile lies here. So let's say one arrow goes like this and the other arrow goes like this. And this is car and not cart. This will be a car and this will be automobile. Now, as humans, we know that it's near to each other. But when we display it under an XY graph or XYZ axis, how do we know that they are connected or they are near to each other? That is where we use something called not this one, something called this angle. And if you're in college, you might know what this angle is. This is a cosine angle. And what we do is have a cosine similarity. Okay. So for every embedding or every vector that we create, we will perform a cosine similarity, which will give us the similarity between two vectors. Okay. The more, the less the value of similarity that we have, the angle value, the more they are similar to each other. Okay. So let's say we have another value, which is like, we'll take up king. Okay, the value is king. And if you want to compare it with what we have as automobile, we have this graph. Sorry, not this one, something like this graph. And if you try to calculate the cosine angle, this becomes very big. Okay, so hence we say that king and automobile are not that similar to each other. And this is basically how the AI understands that the words are similar to each other or not. Okay, so this is the last thing that we do is we have a cosine.ts file where we calculate the cosine similarity. The code is pretty simple. Okay, we take up the two values, which are the numbers. We must have the dimensions of equal length, and then we do a dot multiplication. Okay, this is completely what we say, which is around maths. Okay, so once we are done with dot multiplication, we get the number value here. Okay, so basically cosine similarity helps to get the similarity between the words. Okay, now let us do one thing. I'll create a test file to have a test here to understand how things are working. So this is basically a test file what we did. This is the document that will be passing. The cat drinks the milk. The dog drinks the milk. The cat eats fish. The dog eats meat. The first step to have the one hot encoding to be done here, where we represent each word into a unique vector. Once we have represented into a unique vector, next step is to count the frequency of the word across documents using the bag of words. Okay. Once we have done with the bag of words, we try to reduce the weight of the commonly occurring words with the help of TF-IDF. Once we reduce the weight, we build the co-occurrence matrix, which captures the relationship between the two words. And once we are done with that, we compress the matrix and find and build the embeddings into dense vectors. Okay. And after that, we find the similarity between the words cat, dog, and fish. Okay. Let me go to the terminal. I'll do one thing for this one. I'll have the entire terminal and I'll say npx tsx test list.ts. Okay. Press enter. Okay. Now, if you see, the entire process is being shown to us. Okay. Where did it go? Yes. The first thing is to convert into the vocabulary that we have over here, which is present. Okay. Once we are done with the vocabulary part, we convert the entire thing into vectors. This is the one hot encoding that we do to represent the words in the form of an array. Okay. This is basically one hot encoding. Next is to get it into the bag of words to find the repetition of different words in a particular sentence. Okay. The next one is to get the TF-IDF, which is term frequency and inverse document frequency, to check out if a particular word is repeating in a sentence multiplied by that particular word repeating in number of documents. Okay. And after that, we get into creating the co-occurrence matrix. Okay. To get some relationship between that. Okay, bag of words is done here. If you see here, if you can understand the index value that we have and the vocabulary. The index 0 has the word the, cat has the word cat, something like this. This is for the TF-IDF document. Next, this is how the co-occurrence matrix is looking like. Okay, 0 and 0 does not have any relation. Like the and the is no relation. The cat has a relation. The drinks has no relation. The milk has no relation. The dog has some relation. Okay, so it's like for every index that we have, it's comparing and trying to get some values out of the relationship between those two values here. Next is to get the embeddings generated. So for a particular word, this is the embedding. Cat has this embedding, drinks has this embedding. So everything has that embedding. And the final thing is to do a cosine similarity. And if you see, the cat and dog has similarity value 1 because the angle between cat and dog is almost the same. If you see even the vector representation, the vectors here, it's minus 2.378 and this is also minus 2.378. It's almost the same that we see. Okay. And when we compare with cat and fish, this is fish and this is cat. So the values are changing. Okay. So this is how we get and understand how things are being done. Let us do one thing. Let us finish it off with the help of UI. Okay. So what we'll be doing here is we'll have less, and what we'll do is we'll be using Next.js, okay, for the UI. And I'll just close this. For now, I'll just put the library folder here and I'll say npx create next app at the rate latest and dot. Okay. And then let it start building the Next.js application here. Okay. So this is where we are building the Next.js application and it won't be a longer task. Okay. So we are inside embeddings. Okay. Let it just run till now. And I think we are done. Okay. Inside embeddings, inside app.js, not app.js, app folder, page.tsx, I'll have a complete file here. Okay. Which is a complete UI file. As I said in the beginning of the video that I'll not be focusing on the UI as such because I want to make you guys understand how things work internally to understand the concept behind that. And I'll have the lib folder present here. Okay, I think we are good to go. This is basically the input that we are giving here. Okay, and then splitting the documents, doing the co-occurrence, everything is done here. And this is just the UI. I'll do one thing, npm run def. Okay, it's running under localhost 3001, localhost 3001. Okay, I think this is a hydration warning. I'll just suppress it, suppress hydration warning and reload. Okay. Now, if you see, there are a list of training documents that we are giving. Okay, the cat drinks the milk, the dog drinks the milk, the cat eats fish, the dog eats meat, lion hunts deer, and everything. The first step is to have the one hot encoding. So every word here gets its unique vector. So if you see, the is 1, cat is 0, 1, drinks is 0, 0, 1. So it goes on for all the words that we have. The second part is to have how many times each word appears in every sentence. Okay, so here if we see, there are 8 documents and the word the repeats once in the first sentence. The same goes like for all the other words. So this is how we get tabular representation of the words. Next is to find the common words which become less important while the unique words stay the same and receive higher weights. So the becomes a word which is less important. Hence, it is under the value of minus 0.029 because it's getting repeated and it's a common word. So it's better to remove that. And the word here for we have the cat is 0.245 in the first document. The word fish increases, the value of the word fish increases for 0.347 in the third sentence. Okay, so this is how we are creating the TF-IDF document. Next is to have the words which appear together, having the co-occurrence matrix. The and the is not appearing, the and cat is appearing, something like this. The end-to-end big, tape tab, not tab, the table explaining the co-occurrence matrix. The next thing is what we are doing and representing in the embedding space. Every word is represented as a point in a high dimensional space. For visualization, we are just displaying it in first two dimensions. So if you see here, these are X and Y axis, and these are the points where we are representing the word. And based on the nearest values that we want to take, the similarity of the words depend. Okay. For visualization, as I said, we are displaying the first two dimensions. Let's say we have an embedding visualization tool. Okay. Let's take this one. And what we'll do here is we'll take the documents here and let's try to see how words are related to each other or try to have some different visualization places as well. Okay, we have the indexes. Okay, now if you see, this is basically an embedding model. Okay, where we have the word to vectorization model that we are using. And let's say if we want to search for the word cat. Okay, so now if you see, cat has very different meanings. It has catalans, cattle, located, unification, where the word cat is being used. And this is how the relationship or the dependency of the word is present. Okay, how these words are interrelated to each other. So to find the relation between them, we find the similarity, which is like taking up the 0, 0 point and creating a line over there from one point to the other and finding the cosine relation between them. Okay, so we take that. So this is how the embedding space looks like. So total vocabulary size is 16, documents are 8, embedding dimension is also 8, and the similarity metric is cosine. There are more similarity metrics that we use, but we'll not be talking about that in this particular video. In cosine similarity, we are comparing the two words by measuring the angle between the embedding vectors, as I said. So the cosine similarity between the word cat and cat is 100% because it's almost on the same line. Cat and dog are near, cat and fast is a bit faster, farther from that. Let's say we take the word automobile. So automobile, the car is the nearer to that. Automobile is there. Fast, lion, tiger, drives, deer. We take up, let's say we take tiger. Lion is near, deer is near. Okay. So that is one thing. And these are the most similar words to the word that we choose over here, which is like the tiger. So this is how we have developed an embedding model of our own. So this is basically how you guys can understand how embeddings work internally, right? And this is not a very production ready embedding model that we created, because there are a lot of things that happen internally for different embedding models. And hence, many of the companies have their own embedding models. Like Google has the text embedding model, OpenAI has the OpenAI embedding model. And each of them are made out of different smaller algorithms that we got to understand today. And there are more such detailed algorithms and more such optimized algorithms, which almost reduces the space for the context to be added into the database, because we have to take care of the database as well, right? So this is an implementation of how embeddings are being built. I hope you guys like the way things are going here, because I particularly enjoy building and making this kind of videos where we are actually deep diving into building things from scratch. Okay, so yeah, this was it for the video. Let me know in the comment section of how will you guys improve this embedding model from scratch. Okay, let me know how are you planning to improve this. And yeah, this was it for the video. If you like the video, make sure to like, share, and subscribe to the channel. See you guys in the next one. Until then, bye bye.